Hi, in this video I'm going to tell you about the Norton and Thevenin theories. These theories are about simplifying a linear schematic with one or multiple sources and one or multiple resistors into a simple schematic consisting of just one source and one resistor. These two equivalent circuits look like this. The Thevenin circuit has got one voltage source with a resistor in series, and the Norton equivalent has got a current source with a resistor in parallel. Today we're going to look on how to transform this circuit into both the Thevenin and the Norton equivalent circuits. To start with the Thevenin circuit, we have to calculate two things: the Thevenin voltage and the Thevenin resistance. For the Thevenin voltage, we have to calculate the open source voltage. So that's the voltage that you will measure if you connect a voltage meter directly to the output of the schematic. In this situation, there's no current flowing out of point A from A to B, or the other way around. And so the only current that is flowing through R1, through R2, and then back to the source. The voltage at point A will be the same as the voltage at this point, which I will call point C. These voltages are the same since there is no current flowing from point C to point A, since there's no current flowing from point A to point B, and therefore there will be no voltage drop across R3. So if we know the voltage at point C, we will know the voltage at point A, and therefore we will know the open source voltage, which is the Thevenin voltage. To calculate the open source voltage, we have to calculate the voltage at point C, which, as you can see, is just a simple voltage divider that we have to calculate. So to calculate the voltage at point C, we have to take the input voltage, which is 15 volts in this case, times R2 over the sum of the two resistors, which is R1 plus R2. If we fill in those numbers, we get that 15 times 2k over 2k plus 2k. And as you can see, this is 2 kilo ohms, and this will be 4 kilo ohms. And 2 kilo ohms divided by 4 kilo ohms is a half, so it's 15 times a half is 7.5 volts at point C. So the Thevenin voltage will be 7.5 volts. And from now on we have to calculate to complete the Thevenin circuit, we have to calculate the R Thevenin. But to do so, we first have to calculate the Thevenin current. The Thevenin current is the current that flows in the schematic when the output point A and point B are connected directly with each other. So if you would put an ammeter in between, it will give a certain value. For example, 2 amps, 500 milliamps, whatever. So these 2 points are connected, and the current that is flowing from A to B is the Thevenin current, also known as the short circuit current, when you short circuit the output. And by now our circuit is a bit more complicated, because from now there will be a current flowing through R1 and through R2, but this current will split up, and some of it will flow through R3 and then back to the power supply, to the voltage supply. To do so, we first have to calculate the current that is flowing through the power supply, because that is the total current that's flowing. And the total current is the voltage over the total resistance. As you can see right now, the total resistance is R1 plus R2 and R3 in parallel, since they are both connected to the same node. A and B are shorted, so A and B are connected, and B is connected with the negative side of the voltage supply. So R1 is in series with R2 and R3 in parallel. So we get that for the total resistance is R1 plus R2 and R3 in parallel. And since those two resistors are in parallel, the total resistance is half the resistance of each individual resistor, since they are both the same value. So we get that the total resistance is R1, which is 2 kilo ohms, plus 2 kilo ohms in parallel to 2 kilo ohms is 2 kilo ohms plus 1 kilo ohm, because 2 kilo ohm in parallel to 2 kilo ohms will be 1 kilo ohm, which is 3K. If we want to calculate the current that's flowing, we have to use Ohm's law. So the total current, the I total, is the voltage, V1, over the total resistance, which is 15 volts over 3 kilo ohms, which makes 5 milliamps. So the total current of the voltage supply, the total current is 5 milliamps. As we can see now, not all the current is flowing from A to B. Some current is flowing from C directly to the negative node, and some current is flowing through R3. Since both resistors are the same, the current that flows through R2 is the same as the current that flows through R3. And therefore, the short circuit current is half the total current. Which will then be 2.5 milliamps. The short circuit current is, of course, the Thevenin current. So by now we've already completed most of our unknown values, because we know the Thevenin voltage, we know the Thevenin current, which is 2.5 milliamps. Yeah, there's my scroll bar. But now we have to calculate the Thevenin resistor. To calculate the Thevenin resistor, you have to, for R Thevenin, you have to divide the Thevenin voltage by the Thevenin current. That's why you have to calculate the Thevenin current first. And note that the Thevenin resistance is the same for the Norton as for the Thevenin equivalent circuit. So the resistor in these two circuits has the same value if it applies for the same circuit. So by now we only have to fill in those numbers, so you will get the Thevenin voltage is 7.5 volts, and the current is 2.5 milliamps. If you type that into your calculator, or if you're very good at math, you will see that the total, the R Thevenin, will be 3 kilo ohms. That's how you calculate the equivalent circuit for both the Norton and the Thevenin circuits. I want to note that since this looks like a simplification of reality, lots of people think that this is a very close approximation of reality of the original schematic. But both schematics are exactly the same. If you look at point A and B, you will never know if it is a schematic with just a voltage source and a resistor, or a very complicated schematic. These two schematics behave exactly the same in real world. So thanks for watching.